Hi, welcome back to my channel. In this video, we will be discussing part 2 of Working Stress Design Principle with solve problems and complete solution. For part 2 of Working Stress Design Principle, let us continue solving problem number 1, letter B. This time, instead of 30 kilonewton meter, we will be using, or the concrete is subjected to 70 kilonewton meter. And still, your FC prime is 21, your height is 500, the base is 300 as given, effective depth is also given 425, and your reinforcement are 3 32mm diameter bars. So for step 1, we compute for the cracking moment. Again, we have to relate your cracking moment in terms of bending stress equal to your cracking moment in the NSCP code, which is 0.62 FC prime multiplied by the 0.62, the square root of FC prime multiplied by MCR CP over IG. But if you can remember that this whole process and his still same value would be similar to letter A of problem number 1. Bakit? Kasi the analysis is 500 by 300 pa rin naman siya. And still, the property is 21. Wala masyadong nagbago. Ang nagbago lang is yung external moment na 70. So when we compute your cracking moment would be equal to 35.515 kilonewton meter. Let's store that again on our calculators. For step 2, determine if cracked or uncracked section. To determine the crack or uncracked section, what do we do? Yes, we have to relate your MCR to your MA. In here, comparing the cracking moment to the actual moment, it turns out that your M sub A, which is 70, is now greater your cracking moment, which is 35.515. Therefore, for this problem, we have a cracked section. So what's the importance of your crack section? Importance of the crack section is for us to know the correct way or method in locating our neutral axis. The neutral axis now would be to compute for your x and then for your inertia at neutral axis. To do that, the transformed section would be given as like this. This is the remaining concrete that will sustain compression and will experience stress in terms of compression, and then this is the steel area, which is converted as we multiply your AS to N, which is your modular ratio. Again, your modular ratio would be equal to 9.29, but we need to use the nearest whole number equal to 9.0. Again, AS is computed using 3 32mm bars. The total area is 768 pi square millimeters. Instead of taking the moment at the top of the fiber, we can simplify the equation by taking the moment at your neutral axis. Why? Because we need to locate for your x. Locating for your x is like this. Taking the moment at the neutral axis would result to this equation. If we take the moment, it should be equal to 0, relating those two areas revolving on the same axis. This is area of concrete, Bx, multiplied by its lever arm, x over 2, equated to NAS, area of your steel, multiplied by its lever arm, D minus x. How did we know that? From here, if this is the point where we're taking our moment, this is the local centroid of my concrete, thus distance is x over 2. And from here to there, that's d minus x. Now, putting the values, we can solve for your x. Your x would turn out to be 186.005 millimeters. Let's store that on our calculators. If we locate the global centroid, which is here, we can now say that this is the local centroid of our figure. Please pay attention on the upper left figure. So again, we've seen that your x is 186.005. Now here, if we locate the global centroid, it would be here. And then if we locate for the local centroid, which is the centroid of your concrete, it's there. Why is it important? Because we're now looking for the inertia at neutral axis. All areas should revolve on the neutral axis. Therefore, if there's a distance between the global and the local centroids, we need to transfer them and add that to the gross inertia, which is Ig plus AD squared. In this, there are two areas, the area of the concrete and the area of your steel. Expanding the equation, this would turn out to be bx cubed over 12 plus bx multiplied by x over 2 quantity squared plus n minus as multiplied by d minus x quantity squared. Let's consider that this is, or let's specify that this one is your concrete, this one is your steel. How did we have x over 2? Bx cubed over 12 is the gross inertia of your concrete, base by x. Because it has a local centroid, it has a distance from the global centroid to the local centroid, we need to transfer it with the formula AD squared. Area is bx, distance is, as mentioned, x over 2. Put that into the second power. The steel, it's a strip, so the gross inertia would be negligible. We go straight to AD squared. Since the area is equal to n multiplied by as, the only question now is the distance. From here, which is the local centroid of my steel, up to here, the global centroid, that distance would be d minus x. We express that to the second power, and therefore, we can compute for our I and A. As you remember a while ago, this is what you can just memorize, yung bx cubed over 12. Kasi ito, this figure, when you simplify, it's like this. So either you stick with the concept or you can stick in memorizing this equation. Pero I suggest that you stick with the concept instead of memorizing. Therefore, putting all those values, exact values, I and A would be 1883.850 times 10 to the 6 millimeters to the 4th. Let's store that on C. Now that we have these values, we can now compute for the stresses. Since this is a crack stage, we all know that for a crack section, we have to compute only two values, FC and FS. The given section is like this, as computed is 154.480 and inertia is 1886. For the concrete stress, we're given FC equal to moment multiplied by x multiplied by I and A. Putting those equations into numerical values, this is the value for FC equal to 6.91 megapascals. Next, for steel stress, your steel now is now being stressed up to 79.925 megapascals. So just conserve the positioning of your letters or your unknowns here. Tapos ilagay mo lang yung values and then you can now compute for your Fs. This is a typographical error. It should be F sub S, not F sub C. Note, use exact values when computing stresses and round off only to the final, on your final answers. So these illustrations would clarify on how we can solve stresses on your cracked and your uncracked section. To better practice or to practice more on your understanding and ability to solve problems like this, I'm giving you or leaving you with homework number 1. In homework number 1, there are two major problems. For one, we need to resolve the bending stress in tension and compression of the T-section given below if it is subjected to an external moment, M equal to positive 60 kilonewton per meter, meaning it starts from the bottom going to the top. Number 2, a 350 by 550 millimeter concrete beam is reinforced with 3 25 millimeter diameter bars and is casted with the following information. The diameter of my stirrups is equal to 12. Concrete cover is 40. Determine the properties of the transformed section and calculate the elastic stresses of the given beam if Fc prime is now equal to 27 megapascal. For number 1, let's use 27 megapascal as well. Letter A, if my M is 20 kilonewton meter. Letter B, if my M is equal to 90 kilonewton meter. And letter C, if my M is equal to 110 kilonewton meter. For your submission, copy the problem and upload your answers in the link Homework 1, available in your Blackboard courses. Use bond papers only. You must submit a scanned copy of your answer with complete solution in PDF format only. Once you're done, I'll expect you to submit that within a week, and then we can now proceed with the discussion. I will discuss the whole answer to this problem on the next video, which would be Working Stress Design Principle Part 3. And part of Part 3 would be your singly reinforced rectangular beam, or SRRB, the flexure equation under working strength design. So instead of us memorizing the many steps a while ago, we can just proceed using a flexure equation, wherein your moment due to your compression and then moment due to your tension on concrete and steel, respectively, can be computed by a defined and a simplified equation. I hope that you'll finish your homework as soon as possible, and I hope to see you again on my next video. Thank you again, and bye-bye.